Hi, and thank you for having me. I'm Dr. Eva Sanchez, the lead R&D scientist at Sileto Technologies. And today I'm going to present our work on sustainable polymer concrete production, energy efficient polymerization within a circular economy framework. So throughout this presentation, I'm going to introduce you our core technology from materials to manufacturing to field performance. Concrete is the most widely used material. Okay, thank you. So again, concrete is the most widely used construction material on Earth, but it has a big environmental impact that comes from these factors that you can see on the slide. First, the Portland cement. It requires extremely high kiln temperatures, around 1500 Celsius. So this is one of the most energy demanding industrial processes and a major carbon dioxide source. Second, steel reinforcement. So steel is also energy intensive to produce, and it can include long-term corrosion risks in concrete structures. And third, the water. Traditional concrete consumes billions of gallons of fresh water, and it generates highly alkaline wastewater that requires treatment. So it's clear that all of this is why we need more sustainable alternatives. And here is our product, Sileto. We developed Sileto to bypass these three major bottlenecks. It's a simple non-metallic polymer concrete. So as you can see on this slide, we eliminate cement, so we eliminate kiln-related emissions. We don't use rebar, so we eliminate the corrosion risk. And also, we don't use water in the process, so this simplifies the process itself and eliminates another environmental burden. So Sileto is a simple matrix, just a small fraction of binder combined with sand and powder filler. Next, let's look at how Sileto fits into a circular economy framework. We take waste byproducts from other industries and incorporate them in our aggregate system, like fly ash or rubber from tires, for example, giving them the waste, transforming the waste into a valuable ingredient for our matrix. We are also incorporating bioresin, so the point is to replace petrochemical with something more sustainable, naturally sourced, making this product even more sustainable. It is designed for a long service life, and at the end of life, we can recycle these products because they don't have any rebar inside, so they can be crushed and reused as high-strength ballast, for example. So the point is to use materials that are not only high performance, but also sustainable and responsibly sourced. Okay. On this slide, I want to highlight one of the major advantages of Sileto, that is the zero water manufacturing. So no for mixing, no for curing, nowhere in the process. Because we use a water-free polymer binder, we don't need fresh water in our process, so zero wastewater is generated, making our process even more energy efficient, and when there is no moisture in the matrix, the final product is more durable. Also, in traditional concrete, use steam curing, giant ovens, or some kind of external heat. But the chemistry does the work for us. So our binder triggers a self-heating reaction, and basically the material cures from the inside out. no external heat is needed because it generates just the heat that it needs, the process. So as a consequence, there is a fast strength gain. And as we have this controlled temperature profile, and there is no thermal cracking, and the final matrix is uniform. Okay. So before explaining our new research on green resins, like the incorporation of green resins in our polymer binder, I wanted to set a baseline of our traditional Sileto concrete. And on the left, you can see a comparison of our Sileto concrete with the Portland concrete. And the tensile, flexural, and compressive strengths are significantly higher compared to Portland concrete. This is because we are using an optimized aggregate packing together with a water-free binder, polymer binder that can handle flexural stress that normally would require rebar. Also, the curing time is 14 days versus the 28 days that normally are required. 14 days and even shorter, we are studying this curing time. So think about it at a manufacturing facility with the same production, you will need half the storage area. Also, the porosity is super low compared to the Portland concrete. And this is the difference between a dense protective matrix and one that is open to the elements. So related to this low porosity, we also have low water absorption, low acid reactivity, is an insulator, and a material that is designed to last long. Okay, so the challenge in this project is to keep these impressive numbers while we are incorporating more sustainable materials into the binder. So the challenge is replace synthetic polymers with natural polymers. And as you may know, normally when you do so, it results in a structural penalty. And here is our analytical chemist, Kelly Kurman, that is helping with the experimental part of this green resin project. So here are some preliminary results. They are really preliminary, we are working on it. But it's clear that even when we are incorporating materials from nature, the final product is still strong. I mean, it's comparable to the ultra-high performance concrete. But as I just said, it's preliminary. We are studying how much can we introduce without affecting the mechanical properties. But they are very promising, these results. So to truly validate this material, we perform a comprehensive analysis under heavy haul loads. In 2023, we installed 3 instrumented cross ties, these cross ties here, on a heavy haul line in Brazil, and ran them under 136 train with 40 tons per axle load. Tracking performance over 52 train passes across 10 months. So basically, we install different sensors in different parts of the cross tie and measure the vertical load, stiffness, bending moments, and deflection. And here you can see our cross ties in action. You can see the sensors in this video. And here, the main conclusions are that our material have heavy haul capacity beyond 350 mgt, million gross tons, and improved load distribution, very good ballast to tie contact, high track stiffness that met freight standards, and is also designed for a long service life. So our material and the real trains and real loads perform just how we design it to. It's stiff, reliable, and for long lasting. material. So the railway sleepers is our ultimate stress test. But the beautiful thing about Sileto is its versatility, because we have a material that is immune to corrosion, freeze-thaw cycles, and chemical attacks. Its application expands far beyond the track. So Sileto is zero water, non-metallic, and high-strength material, so it can be used in all the precast and even cast-in-place projects. We are offering a stronger, faster, and a more sustainable option for all the applications that traditional concrete can be used. But to make a real impact, it needs to have an economic sense. And we are aware that we are competing with Portland cement, which is a cheap product. So our strategy to deliver a cost-competitive product is to use low-cost upcycled aggregates without the steel rebar, no water in the process, so no wastewater or wastewater treatment plant. We don't use external heat. Also, we are incorporating green resins or resin from nature that are cheaper compared to a purely synthetic binder. We are recycling and reusing everything that we can in the process. So the fast curing and the circular materials make the commercial production feasible. Ooh, what happened here? This was bigger. Yeah, well, I'm going to tell you. So this was a comparison between Sileto and traditional concrete. So basically, in traditional concrete, there is 1 ton of CO2 for 1 ton of cement, more or less. And Sileto, we don't use cement, so we don't have those emissions. So we don't use rebar, and traditional concrete, normally they use rebar. We don't use water, and traditional concrete uses 450 billion gallons annually. And also we don't use any external heat, and traditional concrete is energy intensive process. And also we are introducing biomaterials into our polymer binder. So the main conclusion is that sustainability and high performance can go hand by hand. So that was it. Thank you for your attention, and I'm happy to take any questions.
We will take all the questions.
Okay, I was fast.
I have 2 concerns. Number 1, it looks like patented material, right? Okay. Is there any publication related to your product?
There are patents related, protecting our product, yes.
Yeah.
And there are more patents on the way.
So it can be only locally used wherever it is available.
When? Say it again.
Can only locally available. It is locally available. We cannot use globally.
Not right now, but we are in the process of doing that, yeah. I mean, we have a pilot plant in Miami, and we are trying to optimize our final product, but the point is to make
No, other parts of the world I'm talking about.
Yeah, I mean...
Outside states.
Yeah, I mean, it could be, because we are focused, our technology is focused on the binder, and you have aggregates even in the desert or everywhere in the world. So if you have the polymer binder that is basically polymer with additives, with initiator or catalyst, you can mix with any sand that you have available in the world and make an awesome product, final product.
Secondly, you have mentioned in one of the slides that there is no need for steel reinforcement.
Mm-hmm.
How it is possible? For example, I am casting beam or slab or column.
Yeah,
So
I
we
mean,
need to have.
It has a very high flexural strength, even without rebar, and this is because of the material itself. I mean, we have like the perfect combination of aggregate packing together with the polymer binder. The polymer binder has different additives to make the trick, to make the magic inside the material. So We can compare, I mean, I can give you some numbers, but we can compare with ultra-high performance concrete.
Yeah,
We have the
even
rebar.
in ultra high performance concrete, we put passive steel reinforcement.
Yeah, I know. I mean, we could use steel, but we don't need to use steel. For example, for cross ties, that is very demanding application, we don't need to use steel.
Okay.
But we could, yeah.
There was
You
another
need it.
question right there. Again, sorry.
On the width.
You actually answered my question. So there really is no steel, no pre-stressing in those railroad cross ties?
No,
Nothing?
nothing.
Wow.
Thank you. On the back, yeah.
Oh, thanks for the presentation. Sileto, right?
Sileto,
Oh,
yeah.
I'm curious about the long-term test, because you mentioned that the railroad test that was carried out was just for 10 months. And,
Yeah.
so I'm just curious to know what, do you plan to carry out a more long-term test, like 2
Yeah.
years, 3 years, to know
Exactly.
the actual durability of the material?
Yeah, yeah, exactly. I mean, actually, those cross ties were installed in 2023 in Brazil, and they are still there. So I think that right now is like 500 million gross tons. So the trains have been passing since 2023, and they are still good, and they are still there. But it's true that we think that it's going to last more than 50 years, but we need to do that study. Our estimation, because we studied in a third-party lab, is that it's going to last more than 50 years, but we need to prove it. I mean, at least the cross ties that are in Brazil, they are still running, and they are in good condition, so that's all I can say.
Any other question?